Swayam Prabha. Digital India. Educated India.
Hello everyone. So, welcome to this sixth lecture of Mineralogy series, and in this lecture we will mostly discuss about the post crystallization processes, and in the last lecture we mostly discuss about the Pauling's second rule, third rule, fourth rule and fifth rule. So, before we start today's lecture, just quickly revise what we have learned from the last lecture. So, in the last lecture we discuss about the Pauling's second rule. So, in this particular second rule, we understand that the bond strength between the cation and anion is very important, and when we try to calculate the bond strength between the cation and anion, we need to know the charge of that particular ion divided by the coordination of that ion. And when we try to calculate the bond strength of different minerals, we observe that there are two different types of situation. The first situation is that when we have exactly the same bond strength, and we have seen in case of our spinel, the bond strength is always same, and when the bond strength is always same, we use a term isodesmic. And so, the spinel group of mineral will have exactly the same bond strength, and the mineral will called as a isodesmic mineral. And there are second situation when we have a non-uniform bond strength, and in that situation our bond strength is not equal in all direction. So, in this non-uniform bond strength, we have observed that there are two different type of scenario. So, first situation is that when the bond strength between the anion and cation is exactly the half of the charge of the coordinating anion. So, when we have this kind of situation, we call that one as a mesodesmic. So, we have seen that in case of silicates, for example, garnet or olivine, we have a mesodesmic kind of situation. Then we have a second situation in non-uniform bond strength, and in that one we have a anion cation bond strength is exactly, some of the anion cation bond strength is exactly the half of the charge of your anion. So, we have seen the example in case of when we have anion cation bond strength is more than half of the charge of the anion. So, in that case situation we have an isodesmic kind of scenario, and we have seen that we have a carbonate, and carbonate we have a bond strength is always more than half of the charge of the coordinating oxygen. So, this was the second law, and in the third law we try to understand when we bring two tetrahedra together. So, there will be always some kind of repulsion between cations which has a larger charge and smaller coordination number. So, when we try to bring together these two tetrahedra, so what will happen that we have a three different situation. Either we can connect them from the apices, or we can connect them for the edges, or we can connect them from the faces. So, we have seen that when we bring together this tetrahedra from the apices, so the distance is if we consider as a 1 unit, so that is the most stable configuration. And in the geology, in mineralogy, we have seen that many different minerals have this kind of structure. But when we try to connect the two tetrahedra from the edges, so our distance between the two cations are decreased, and there will be some kind of repulsion force, and this repulsion force will create some kind of distortion or some kind of distortion in the structure, and because of that we will have less stable structure, and there will be some kind of repulsion. And when we try to connect with with faces of two tetrahedra. So, what will happen that the distance between the cation will reduce to they will bring quite close to each other, and there will be a strong repulsion, and because of that this structure will not stable, and this situation we will not find in nature. And we also compare this with a octahedron, and when we bring the octahedron, we have seen when we connect the corners of the octahedron. So, it is easily we will find this kind of structure, because the coordinating this cation has a smaller charge, and the distance between two cations will be one unit. So, when we try to connect the edges or the faces, so still when we try to connect the face of the two octahedra, so what we have observed that the distance is almost like a still we have a quite a distance. So, your two cations are placed at a distance, so that in when we try to connect the faces of the octahedra, there is still a stable structure compared to the tetrahedra. So, this is the third law of your Pauling, and the fourth law of Pauling is an extension of the third law. And according to this law, when we have a cation which is has a larger vacancy and smaller coordination number, they try to not connect with a other polyhedra. If they try to connect with another polyhedra, so in that case the structure will be either distorted or twisted. So, we have seen two example. First example was Alvin, where you have a isolated tetrahedra, and then there is a second situation was perovskite, and in the perovskite the silicon will be coordinated will be connected from the corners. So, because of that there is some kind of a distortion in the structure, and because of that your perovskite structure is not a perfectly cubic structure when we talk about the magnesium perovskite. So, this is the fourth law of Pauling, and the last law, fifth law of Pauling, basically suggests the law of parsimony. According to this law, according to this rule, when you have a mineral, and in the mineral you have a only limited number of sites, and in this limited number of sites the number of different cations will go to this limited number of sites. So, we have seen the example of amphibole. In amphibole there are 5 different sites, and in this 5 different sites, even though Alvin amphibole can accommodate many different types of cation and ionic group, but these different cation and ionic group will go to these 5 different sites. So, because of that this many different cations will go to the same side, and they will make some kind of solid solution. So, this was the last law of Pauling, and today's lecture we will mostly discuss about the post crystallization process. And so, in this post crystallization process, what happens that already in the Earth's interior you already have crystals, and when you have a crystals, so they are stable at particular pressure and temperature condition. So, when you try to put some kind of when you change the pressure and temperature, and how you are going to change the pressure and temperature? Suppose if you put that material through the convection, so you bring that material to the interior of the Earth, or suppose you have a stable mineral at particular PT condition, and you put that material through subduction to the interior of the Earth. So, what will happen that when your material will go to the interior of the Earth, so basically your material will interact with the surrounding, and what will change? Your pressure and temperature condition will change. So, when your pressure and temperature condition will change, so whatever bonds are present inside the mineral structure, they will either rearrange or they will break, and they will form some new crystal structure, or there will be some kind of a structural transformation. In this case, your mineral is in the solid state. So, this transformation will be in a solid state. So, there will be no liquid. So, your solid mineral 1 or high pressure, this low pressure solid phase will change to the high pressure solid phase, and in this situation what will change? Your pressure or temperature will change, and when your pressure and temperature will change, their internal arrangement will either reconstruct or displace, and because of that the new mineral will form. Okay. So, if you have this kind of situation, we call this kind of reaction we call as a polymorphism. So, basically in polymorphism you have a same chemical composition, but their minerals, their structural or atomic arrangement are changed. Okay. So, polymorphism is derived from the Greek word. So, poly basically means many and morphism means form. So, when a mineral has more than one form and their chemical composition is same, so we call this type of mineral as a polymorphic mineral. So, this polymorphism is happen due to the change in pressure and temperature or both. Okay. And there are different examples of polymorphism, and when we talk about in terms of mineralogy, so all these different phases have a different structure. So, if you see the example, there is an example of polymorphism is a diamond which has a composition of carbon. So, C, and graphite which has a composition of carbon. So, both these phases have a same chemical composition, but if you see the internal arrangement, if you see the crystal structure of your diamond and graphite, so basically their crystal structures are different. So, because when you apply a pressure, mostly pressure, so your graphite will change to diamond. So, we will try to understand this in more detail. Okay. But before we try to understand the polymorphism in detail and what are the different types of polymorphism, we should try to understand why a constant chemical composition may have a different structural arrangement. Okay. To understand this, we should a little bit know about some basic terminology in thermodynamics, and we should try to understand that when we talk about thermodynamics, so thermodynamics is a study of energy. Okay. So, we basically study the different types of energy. Before we try to understand that why different phases will be stable at different pressure and temperature condition, we should define few terms. For example, the first term is this phase. Okay. So, when we talk about phase in geology or in mineralogy, so your phase is anything that define any part of the universe which can be defined thermodynamically. For example, suppose if you have a crust or you have a mantle, okay, or you have anything, suppose you have a crust. Okay. So, you can basically define a crust. So, you basically define a boundary. Okay. So, in a system, so before we try to understand a different structure, so before we try to understand the why we have a different structure at different pressure. So, before that we should try to understand few thermodynamics terms, and we know that in thermodynamics we basically interested in a energy of a study of a energy, and when we talk about energy, first we have to define a system. So, we have to define a system, and system defines any part of the universe basically which can be defined thermodynamically. For example, if you want to define a system, so you should know that that system has a boundary, okay, and it can be anything that can be present in this universe. So, for example, it can be any layer of the earth. For example, it could be a crust, or it could be a mantle, or it could be any rock. So, if you can define the boundary, real or hypothetical, okay, in that is a part of our universe. So, that will be a system. So, it can be a crust. So, or it can be a rock that is present in the crust, or in different minerals that are present in that rock. So, anything could be your system. So, system is basically is a part of our universe, and that is defined by us or by a user. So, suppose if you take a rock, if you have a metamorphic rock, or you have a sedimentary rock, and in this sedimentary and metamorphic rock you have a different layers. So, suppose you have a different layers, different bands of minerals. So, you can define the whole rock. So, if you can define the boundary of the rock, so that could be a system. Or you can take a band in that particular rock. Suppose one band is made up of a light color mineral and another band is made up of a dark color mineral. So, if you can define the boundary of the light color mineral, so that could be also a of your system. So, you can divide this system into so you can define a system that a bright color mineral is present, that is your system, or a dark color mineral, that could be your system. So, that is a system. So, when we talk about system, there are three different types of system in geology. So, we have a isolated system. So, we have a isolated system. So, in isolated system, basically there is a no exchange of energy and mass. So, there is a no exchange in energy and mass. So, basically your system is completely isolated compared to its surrounding. So, compared to its surrounding, there is a no exchange of energy and mass. So, when you have this kind of situation, okay, we call that system as a isolated system. So, isolated system is very difficult to find in nature, but this system is very useful to derive a different formula or different. So, for the theoretical calculation, these systems are very important. You have another type of system, that is your closed system. So, you have a closed system, and in your closed system, basically energy is exchanged, but mass is constant. Okay. So, there is a no mass is same. So, basically your energy is exchange. So, energy, but mass is always constant. So, basically you do not change the composition. So, your composition is constant compared to its surrounding. So, basically when you have this kind of situation, you have a closed system, and there is a third type of system, that is a open system. And in open system, your there is a exchange of energy and mass together compared to its surroundings. So, there is a constant exchange of energy and mass, and in geology you have a closed system and also you have a open system, and we always try to study the closed system. So, in the closed system you it is easy to understand. So, because of that we start with a closed system, but in nature if you see, we have a open system. So, there are three different types of system. The second term which is important to understand is your phase. So, phase is So, basically your phase in a system has a distinct physical property and chemical characteristic compared to its surrounding. So, suppose we have a peridotite. So, when we have a peridotite, suppose you have a system and in this system you have a peridotite rock, and in peridotite rock we have a different minerals. So, suppose we have a garnet, we have a olivine, we have a orthopyroxene, and we have a suppose some clinopyroxene. So, basically all these minerals we have a typical physical property and it has a different chemical composition. So, you can basically separate different phases from each other. So, you can mechanically separate this olivine from garnet, from OPX and from CPX. So, when you have this kind of situation, so this situation is in this case you can distinguish a different phases. Okay. So, you can mechanically separate that particular phase. So, this is a phase, and the another important term is your component. So, when we talk about component, so basically your component has a two different meaning. So, we have a component. So, we have suppose a component which is derived by the distinct chemical composition. So, suppose we have a mineral, mineral is your Mg Fe2 SiO4. So, we know that this mineral is your olivine. So, we have a olivine, and your MgFe has a 6-fold coordination, and this silicon has a 4-fold coordination. So, this is a mineral formula of olivine, and we know that this olivine has a 2 end members. So, first is your magnesium end member, and second one end member is your iron end member, and this magnesium end member is known as a phosphorite and iron end member is known as a phyalite. So, basically your this phosphorite and phyalite is a component in your phase olivine. So, basically this the olivine phase, the single phase has a 2 component, and this component is defined by the distinct chemical composition. And when you have a single phase, so that single phase is defined by the mixing of these 2 component at any proportion. So, you have a 100% Mg or 0% Fe end member to a 0% Mg end member or 100% Fe end member in your olivine formula. Okay. If you take another example, for example, if you take another example, that is your Mg, Fe, calcium, Mn, 3Al2 Si3O12. So, this is the formula of your garnet, and in this garnet if you want to define a component, so you can have a Mg3 Al2 Si3O12 or Fe3, that is in 2 plus state, Al2 Si3O12 or calcium 3 Al2 Si3O12 or Mn3 Al2 Si3 O12, and these 4 components are defined as pyrope, you have a almandine, then you have a grossular, and this is a spacetine. So, you have this 4 different component. If you want to define this one phase of this single phase of this garnet, you can define by using this 4 component. So, you can place this 4 component and you can define this phase. So, in this system you have a one phase and 4 different component. If you take an example of, for example, quartz, formula is SiO2. So, the quartz is a single phase, and if you see the component in quartz, you have a single component. Okay. So, here your phase and component is 1. Okay. But suppose if you have a quartz and you have another mineral, that is your corundum, and the formula of corundum is this. So, if you have a rock in which you have a quartz and corundum. Okay. So, when you have 2 different phases in this particular rock, okay, so to define the phase, you can define either your component is SiO2 and Al2O3, okay, or you can also take this different ions or elements, that is your silicon, aluminum and oxygen. So, if you take this quartz and SiO2 and Al2 as a component, so your component here will be 2. If you take a Si as a component, aluminum as another component and oxygen as another component, so your component here will be 3. So, basically it depends on a system that you take the component that are those that describe the chemical variability of a phase or a system, okay, and which is composed of a one or multiple phases. Okay. So, because here your component is 2, so basically we will use this SiO2 as a one component and Al2O3 as a 2 component. Similarly, you can take some other example, for example, in case of your sillimanite or andalusite. So, you have a formula of Al2SiO5. So, this is a sillimanite. So, you can take this your Al2SiO5 as a component. So, if you take that as a component, so this is a one component system, okay, or you can take Al2O3 and SiO2, that is a 2 different components. So, Al2 as a one component, Si2 as another component. So, component is 2, or you can take Si as a component, aluminum as a component and oxygen as a component. So, your component will be 3. Okay. But here your component is minimum number of component. If we take Al2SiO5, that is 1. So, in this situation this number of component in this system will be 1. So, that is the minimum number of component. So, basically we have 2 different types of component. One component is known as your phase component, the component of the phase, and another component is a component of a system, and which is basically defined by the chemical variability of the phases, which is composed of a one or multiple phases. So, this is about the component, and to know about the free energy. Okay. So, if we want to see that when we have there is a effect of pressure or temperature, and because of that there is a breakage of bond or rearrangement of bond. So, we have a different crystal structure. So, we try to understand why this different structure at different PT conditions are stable, and this is basically because of that particular phase has a lowest free energy. Okay. And we want to define a free energy. So, this free energy was originally derived by the J. Willard Gibbs, and he was an American scientist, and we know that this Gibbs free energy can be defined by you can write this equation G is equal to H minus T s plus P v plus R t ln A, okay, where your H is your enthalpy, and your enthalpy is total amount of heat of your system, okay, and the heat content of the system. T is your temperature, okay, and S is your enthalpy, okay, and this S is your entropy, sorry. So, entropy is your degree of randomness. So, when we have a phase at high temperature, so that phase will have a higher degree of randomness. So, your entropy will be higher. When a phase is stable at a lower temperature, so your degree of randomness is lower. So, your phase will have a lower entropy. Then we have a P, that is a pressure, this is a volume, and in mineralogy we mostly, in thermodynamics, in geology, we mostly deal with a molar volume. Okay. So, this is a volume, and then we have a R, which is a gas constant, then we have a temperature, and there is a term which is A, this is a activity, and define a activity. If you want to define a activity, so basically your activity of any phase suppose you have an activity. So, you can define that if you know the mole fraction, that is your mole fraction of component I in suppose phase phi, okay, multiply by gamma I phi. Okay. So, if you want to define activity which is a function of your mole fraction of component I in phase phi, okay, and this gamma is your activity coefficient, okay, the activity coefficient of component I in phase phi. Okay. So, basically if you have, suppose if you try to derive the activity of component I in phase phi. So, basically this is phi. If you want to derive this, and in terms of your mole fraction, that is a component I in phase phi. So, in case of your ideal solution, your activity will be like this. So, in that case your gamma I phi will be always 1. So, in case of your ideal solution, okay. When your system is not ideal, okay, so basically when your this gamma I phi is equal to 1, and when you have a ideal solution, so in that case your activity of component I in phase phi will be equal to the mole fraction of component I in phase phi. Okay. So, that will be both activity and mole fraction will be equal. Okay. When your system is non-ideal, okay, so you have a two different situation. One situation, your non-ideal solution will have a graph like this, and in that situation your gamma I phi is not equal to 1. And when this is the situation, your activity of I phi will be always more than the x I phi. Okay. So, we have always activity is more than the mole fraction of that component in phase phi. You have a second situation when your non-ideal solution will activity and mole fraction will change like this. This is also situation when your phi, this gamma I of component I in phase phi is not equal to 1 and it is a non-ideal solution. So, you have a non-ideal solution, and in this situation also your activity in this situation your activity of component I in phase phi will be less than the mole fraction of component I in phase phi. Okay. So, you have a two different type of situation. Okay. So, basically if you write down, if you change this term and if you replace this mole fraction and activity coefficient, you replace this activity with in terms of your mole fraction and activity coefficient. So, you can rewrite this equation 1 like G is equal to H minus T s plus P v plus R t ln, then you have a x I and you can multiply this with your gamma I. Okay. But in case for ideal solution, if we take ideal solution, if we take ideal solution, so in that case your this gamma I will be equal to 1. When gamma I is equal to 1, so you can rewrite this free energy as a H minus T s plus P v plus R t ln x I. So, basically you can derive this free energy, gives free energy in terms of enthalpy, in terms of your entropy, volume and your mole fraction of component I in that particular phase. Okay. If suppose we are talking in terms of a very low pressure condition, so we can ignore this term, and for simplicity we can rewrite this equation as a G is equal to H minus T s plus R t ln x I. Okay. If we take a pure phase, when we take a pure phase, in that case your this x I will be equal to 1, because in case of pure phase your x I will be 1 and this term, because this is 1. So, ln 1 equal to 0. So, this whole term will become a 0. So, basically if we talk about the free energy of a phase at a very low pressure, so that will be a function of your H minus T s. Okay. So, this is the free energy of a system, and you can see from this equation that your free energy is a function of your H and T s. So, basically when you increase the temperature, because this temperature is in minus term. So, when you increase the temperature, your free energy will decrease. Okay. So, if we take suppose a phase low quartz and high quartz. Suppose we have a low quartz, that is a alpha quartz, which is the most stable form of quartz at a crust. So, if we take a alpha quartz, okay, and if we suppose define this in terms of free gift free energy and temperature, because this is a function of your when we increase a temperature, gift free energy is decreasing. So, it has a negative slope. So, suppose at particular temperature the alpha phase has a particular gift free energy, and when we increase the temperature, because it has a negative slope, so it will have a this particular energy, this particular free energy. And if we take suppose another phase, this is a beta phase. So, beta phase is your high quartz, that is a stable at high temperature. So, definitely at low temperature your beta phase will have a higher free energy, and because of that your alpha quartz is stable. So, if you see the slope of your beta quartz, okay, so beta quartz slope will be always steeper than the alpha quartz, because if you see the at high temperature your degree of randomness is high. So, basically when you write down this, so at high temperature when you increase the temperature your randomness is high. So, this term is greater compared to the low temperature. So, when this term is greater you have a smaller value of your free energy, and because of that when you define a slope of your beta phase, okay, so slope of your beta phase will be always steeper than your this alpha quartz. Okay. So, at high temperature your beta phase will be stable because it has a higher it has a steep slope and its free energy is lower. I am deriving this as a straight line, but in nature you always have a curve, and at a particular point in this curve if you draw a tangent and if you measure the slope. So, that slope, that particular intersection of the slope at the tangent will be give you the value of the free energy at particular temperature, but for simplicity I am drawing this as a straight line. So, basically there is a change in free energy. So, that can be defined as a delta G, okay. And so, at high temperature, when you increase the temperature, so you see that your beta quartz is stable and this will have a negative value. In case of a lower temperature, this delta G will have a positive value, and at this point where your these two phases, this alpha quartz and beta quartz are intersecting, that is basically a temperature, that is a melting temperature of this system. Okay. So, basically when you go from low temperature to high temperature, when you go from this temperature to this temperature, you basically increase the temperature. So, you are basically giving a energy to the system, and when you are giving a energy to the system, you are basically increasing the degree of randomness in beta phase more, and because of that you have this beta phase is stable. So, but what happens that in nature when your beta phase is stable, okay, so in both the system your basically both has a hexagonal structure, and when you supply a heat to the system, alpha quartz is immediately changes to beta quartz, but when you release a temperature, and when you decrease the temperature, so energy is dissipated, and because of that because this alpha quartz and beta quartz, so beta quartz has a very small activation energy. So, what happens that immediately this beta quartz is changes to the alpha quartz. So, when you have this kind of situation, so your polymorphism is called as a displacive polymorphism. So, if we see the different types of polymorphism. So, we have a first type of polymorphism that is known as a reconstructive polymorphism. So, basically in reconstructive polymorphism, we are applying a energy to the system, we are giving a energy to the system, and the bonds which are present in the mineral are basically reconstructed. So, you break the bond inside the crystal structure and the new bonds are forming. So, their crystal structure is completely changes, and because of that we have a reconstructive polymorphism, and in this system you have a very high, you need a very high activation or very high amount of energy is required, because we are basically breaking a bonds. Then we have a second type of, and the example is your graphite to diamond transition. The second type of polymorphism is your displacive polymorphism, and in the displacive polymorphism we are applying a very small amount of energy and we are not breaking the bond, but we basically rearranging the different bonds present in the crystal structure, and because of the rearrangement and displacement you have a displacive polymorphism, and the example is your alpha quartz to beta quartz. The third type of polymorphism is order disorder polymorphism, and in this order disorder polymorphism is important when we apply a temperature in the system, okay. And when we apply a temperature in the system at a high temperature, we have a very high vibrational energy, because your atoms are vibrating at higher temperature, we have a more higher degree of randomness. So, in that case any of the cations or ions present in the crystal structure can go to the different this atomic sites, structural sites. But in case of lower temperature, because vibration is very low, your structure is more order. So, your atoms will go to the particular site, and because of that you have a order polymorphism. An example is your K feldspar. So, these are the some example of reconstructive polymorphism. For example, you have a diamond and graphite. So, graphite will always transform to diamond, and if you see their crystal structure and their space groups are also different, okay. Also their physical properties are also different. If you see, diamond is the hardest natural occurring material, and graphite is one of the softest materials. So, their physical property also changes when there is a reconstructive polymorphism or other type of polymorphism. Their specific gravity is also changed. So, another example is calcite to aragonite, and if you see, calcite will always form in the rhombohedral system, and aragonite will form in the orthorhombic crystal system, and their hardness is slightly different and their specific gravity is also different. If we see the reconstructive polymorphism, so in this reconstructive polymorphism basically we break the bonds, and because of the breaking of the bond we have a completely new crystal structure, okay. And to break this bond we need a very high amount of energy, and this energy is basically must exceed the activation energy. So, if you see the energy, if you see the energy, so if you see the energy and if you put suppose a graphite here, okay, and diamond here, okay, diamond here. So, if you see the energy of your graphite, so graphite has a at 1 atmospheric pressure, okay. Graphite always have a lower energy, okay. Because of that, graphite is the most stable phase in the atmospheric pressure. If you see the free energy of or the energy of diamond at 1 atmosphere, it is always higher than the your energy of the graphite. But if you see the graph, so your graph is something like that, and if you see when you bring the diamond from, so we know that diamond has a isometric structure, and we have a carbon which is coordinated in a 4-fold coordination, and we have learned about this. So, diamond will be stable more than 5 gigapascal pressure and 1500 degree C. So, if you see if you compare with a geotherm gradient, so your diamond will be stable at this point, okay, at this particular depth. So, when you bring this diamond, to the surface, okay, when you bring the diamond to the surface, when you decrease the pressure. So, when you bring, what happens that because diamond has a higher free energy, but to get back to the graphite structure, it needs this amount of energy to cross, okay, and this energy is a barrier, and this barrier energy is known as a activation energy. Activation energy, because the diamond has a large activation energy, and because of that it cannot, the diamond which is stable here has a higher energy, it cannot cross this barrier. So, because of that it will survive in a low pressure, and what will happen that the reaction, the back reaction from diamond to graphite will be very slow and very sluggish. So, it will take a very long time. So, if you keep a diamond at a room pressure at one place and you return after several million years after, so you will find that maybe billion years after, you will find that diamond is changes to graphite. So, graphite, because it is a high pressure form of carbon, but because their activation energy is very high, but it is stable in a room pressure condition. So, it is called as a metastable phase. So, similarly you can find your tridymite, or you have a cristobalite, which is a high temperature polymorph of your quartz, that is also stable in a room temperature condition. Okay. So, there is another so if you see the energy versus temperature, if you plot your energy versus temperature in case of your reconstructive polymorphism. So, what will happen that when you have a, so energy is increasing from bottom to top and from left to right, temperature is increasing. So, suppose you have a phase which is stable from one temperature to another temperature, okay, and after certain temperature their bonds will break, and when their bonds will break, they will form a new type of crystal structure. So, what will happen that you will see there is an abrupt change in energy, and then this point will know as a reaction temperature. This is your reaction temperature, okay. And when you already break the bonds at this particular temperature, so from this temperature there will be a sudden increase in energy, and from this energy your polymorphic phase will be stable. So, here your phase 1 is stable, here your phase 2 is stable, okay, and this point is known as a reaction temperature. You can draw a similar thing in terms of pressure. So, in pressure, when we talk about pressure, we mostly plot a molar volume. So, molar volume. So, your molar volume is increasing in this direction, and molar volume is the volume occupied by a substance by 1 mole of the substance. So, basically when you increase pressure, your volume is decreasing. So, basically you have at certain pressure you have a value of molar volume of a phase 1, and after a certain pressure you will see there is a drop in a molar volume, and then there is a abrupt change in a molar volume, and this is known as a reaction pressure. So, this is your reaction pressure, and after that your phase 2 will be stable. So, your phase 2 will be stable. So, this is the situation of your reconstructive polymorphism, where you see there is an abrupt change in energy after certain pressure and temperature. Similarly, you can see in case of your displacive polymorphism, if you plot your energy versus temperature in your displacive polymorphism. So, in case of reconstructive polymorphism, you see there is an abrupt change in energy, but in case of your energy versus temperature, so it has some kind of change in energy when you increase the temperature. So, in this temperature range, your phase 1 is stable, but after this temperature, your phase 2 is stable. Okay. So, like in case of reconstructive polymorphism, you can see there is a abrupt change in energy, but here there is some kind of discontinuity. Okay. So, you can identify that discontinuity, but there will be no abrupt change in energy. Okay. Similarly, if you plot this energy versus if you plot the molar volume versus a pressure. Okay. So, similarly, you see your phase 1 and phase 2, there will be a discontinuity, there will be no abrupt change in molar volume. So, in case of your displacive polymorphism, you need a very little amount of energy to just rearrange the bonds. Okay. So, you basically rearrange the bond, so internal arrangement is required, and to make this kind of changes you need a very small amount of energy. Okay. So, you basically displace the atom and there is a bond stretching and shrinking, there is no breaking in this kind of polymorphism, and you need a very small amount of activation energy. Because of that, your beta quartz is always changes to alpha quartz, because activation energy of beta quartz is very small, and there are different types of polymorphic phases are present in this SiO2. So, these are the high pressure polymorph of SiO2, and Stishovite has a formula, all these phases have a formula of SiO2, but Stishovite has a 6-fold coordination. Okay. All other phase will have a 4-fold coordination, and they will form in a tetragonal structure. Coesite will have a monoclinic structure, and in this, when you increase the temperature, you will have a alpha quartz through beta quartz, and this will, in this one, when you have a alpha quartz which is a low quartz. So, low quartz you have a higher symmetry, but when you increase the temperature, it changes to a beta quartz and it will have a lower symmetry. So, but because they have a lower activation energy, so because of that your beta quartz will change to the alpha quartz, and because of that in nature you mostly find a alpha quartz, not beta quartz. So, in this case, in the displacive polymorphism, there is a rearrangement of bond angle between the atoms. So, this is the example. There is a third type of polymorphism, that is the order disorder polymorphism, and in this order disorder polymorphism, what happens that when your crystal is perfectly ordered, okay, so that is perfectly ordered at a absolute 0 temperature. Absolute 0 temperature is a 0 Kelvin, means that minus 273 degrees Celsius, and we know that most of the material which we find in nature is formed at a relatively much higher temperature. So, we have a perfect order at a absolute 0 temperature, Kelvin temperature, but in nature, because most of the materials are formed at a higher temperature, so we have a higher temperature condition. And if you see the perfect order, so what will happen, that in your crystal structure you basically have a structure side 1 and a structure side 2. So, there is a 1 2, so there is a ordered structure, okay, 1 2, and similarly here you have a 2 1 2. So, you have a some ordered structure, and this different specific structure sides, in this specific structure side specific atom will go. Okay. So, suppose you have a atom A which is shown by the gray color and the white this circle, this is a B atom. So, in the structure site 1 your atom A will go and structure site 2 your atom V will go. When you have this kind of arrangement, you have a perfect order. Okay. In case of total disorder, and this will happen at a low temperature, okay, which is a absolute 0 condition or relatively at low temperature. When your structure is completely disordered, so in that case what will happen, that because you have a two different structural site and probability to have a atom A in structure site 1 is 50% and probability to have a structure site 2 probability to have a atom B in structure site 1 is 50%, because at high temperature your structure will be completely, your atoms will be completely vibrating. So, there will be high degree of disorder and randomness. So, in any side any this atom can be go. So, in this type of situation you have a total disorder and this will be at high temperature. Okay. In between you have a partial order in which some of the sites will be filled by maybe site 1 will be filled by atom B or atom A. So, there will be some kind of mismatch. So, when you have some kind of mismatch in particular site, you have a partial disorder. So, partial order or partial disorder. So, the best example of your order disorder is in a K-feldspar. So, if you see the K-feldspar is a framework silicate, and in the framework silicate is a tectosilicate. So, all the corners are shared. So, in that structure, in that mineral, you have a 4 asymmetric tetrahedral site. So, you have a tetrahedral site 1, 2, 3, 4. So, you have a 4 tetrahedral site, and in this tetrahedral site, when you see at a low temperature, okay, when you see at a low temperature, what will happen, that because at low temperature the vibration of the atoms will be low. So, your particular this aluminum, if you see the formula of your this K-feldspar, so you have a KAlSi 3O8 and aluminum and silica both are 4-fold coordination. So, they have a 4-fold coordination. So, basically you have a 3 silicon atom and 1 aluminum atom. So, basically at a low temperature, essentially what will happen, that at low temperature, because your structure will be perfectly ordered, so your aluminum will go to the particular side and all 3 other tetrahedral side you will have a silicon. Okay. Because in this side aluminum will go, because very close to this you have some potassium. So, because of that the exchange reaction will be balanced. So, it has a 3 plus and it has a plus 1. So, because it will make some kind of solid solution. So, because of this particular site aluminum will fit, but at high temperature what will happen, that any of this 4 tetrahedral asymmetric tetrahedral site, this aluminum can go. So, aluminum can go here, aluminum can go here, aluminum can go here, aluminum can go here. So, the probability to have a aluminum in this 4 different tetrahedral site in the high temperature is 25%. Okay. Here in low temperature, the 100% probability to have a aluminum at this particular site. Okay. So, this is the example of your order disorder. So, this is because of that, because at high temperature you form a cyanidine, which is a high temperature polymorph of your K-feldspar. So, this aluminum can substitute for any silicon and it is a completely disordered structure, and microcline will form at a low temperature and this aluminum will go to the one particular site. Okay. So, this is the example of your order disorder. So, when you get a cyanidine in your rock, so you should immediately understand that this rock is formed at a very high temperature, but if you find a microcline, so you should understand that your rock is formed at a relatively lower temperature. So, this concept is very helpful to understand the temperature condition of the system. and order disorder is related with a temperature of your system. So, I think I will stop my lecture here, and in the next lecture we will try to understand about the phase relation of the binary system. So, thank you.